Hello friends, I am Nikita and you are watching Prepare for GATE. GATE is a competitive examination conducted every year by 7 IITs and 1 IISc. In total, 8 organizations conduct this examination every year. With this year, IIT Guwahati is conducting. So moving on, seeing the great organizations conducting this exam, let's discuss the topic that we'll be discussing today. We'll be covering angle modulation and demodulation, spectra of AM and FM. Not AM. AM I have already taken up in my last video. This time, spectra of FM. Okay. This will be the topic of discussion: angle modulation, narrowband FM, wideband FM, and phase modulation, demodulation, spectra of FM, phase log loop, and gate questions. The instantaneous frequency and phase. Before calculating what is an FM signal and a phase signal, we must know the instantaneous frequencies and phase values, how to calculate them, how to get and from an PM signal an instantaneous phase frequency, and from an FM signal an instantaneous phase. So we have already known that phi t is AT cos pi t plus theta, but here I have shortened this expression and used a constant amplitude because the amplitude is not variable in frequency and phase modulation. That used to be the case only in amplitude modulation. And then theta t. Yes, in this case the frequency, the phase will be variable. So if we take the instantaneous phase, we can calculate it by minus omega t minus infinity to t omega a. Okay. Now this is the formula to calculate phase. So the phase would be omega ct plus k mt. The instantaneous frequency we can get by differentiating the phase, and we get omega c plus with the dot I have shown that it's a differentiation, where k is the frequency deviation. In the linear modulation, the information was present in the amplitude of the message signal, whereas in angle modulation, the carrier frequency component of an FM wave contains part of the message information. Okay. So in this case, it is the carrier wave itself, the zero crossing of the carrier waves, I must say, that contains the information. A basic PM signal expression would be phi t a cos theta t. The instantaneous phase in this relation will be omega ct plus kp mt, and the instantaneous frequency can be calculated by differentiating the phase. An instantaneous frequency expression would be omega it is omega c plus af mt, and the instantaneous phase can be calculated by integrating the instantaneous frequency expression, and we get this final frequency modulation FM signal, which the M of alpha, the message signal, is actually the integration and added with the carrier frequency. Now this is a very important method, termed as direct method, where in first case, if we wish to have a frequency modulator, then what we do, if we integrate a message signal and pass it with a phase modulator, we'll get a frequency modulator. And if we differentiate a signal and pass it to a frequency modulator, we get a phase modulator. That is important and crucial to remember. Now let's look at gate NCT 2017 question. It's very interesting. Okay. A modulating signal given by xt 5 sine 4 pi 10 to the power 3t minus 10 pi cos 2 pi 10 to the power 3t volts is fed to a phase modulator with a phase deviation kp 5 radian per volt, and if the carrier frequency is 20 kHz, the instantaneous frequency at t equals to 0.5 milliseconds. You need to calculate instantaneous frequency. The formula for instantaneous frequency, we have already known that if a phase deviation is given, and you'll see that this whole function, if we take this as phase, then if we integrate this, like we differentiate this phase, okay, if we differentiate this phase, we will get m and then multiply with kp, okay, and then multiply with kp and add the omega c value we'll get our instantaneous frequency. Okay, so let's start. It's given that kp fc, we know that instantaneous frequency of phi is fc plus kp by 2 pi. 2 pi is mentioned over here because of being converted from radian per second to just per second, and differentiation of mesosecond. Now differentiate mt with respect to t. We get this whole expression with the help of product differentiation. Okay, at 0.5 millisecond we get this value, and on substituting different values into this equation we get our final 70 kHz value. Okay, a very simple, very easy approach to find instantaneous and phase of a signal. Okay, now let's go. If you say the power of the angle modulated signal is a square by 2, it is almost remains this throughout, because you can see that the amplitude is not changing. Amplitude is remaining the same, and amplitude is the main parameter on which the power of the signal is considered. Okay, so here I have shown you an AM signal AM signal frequency band. To recall that what we have learned is this. This is a double side band with the x of t expression, this. But a narrow FM is very similar to AM signal with a small changes, that if you put all this value, right, beta is equal to sin omega m, you will notice that the magnitude at omega c minus omega n frequency is negative, with a reverse amplitude at fc minus fm, rest is all the same like that of the AM signal. So this is a small change that we find in a narrowband FM spectrum. The wideband FM spectrum. The expanded FM expression x of t is a by 2 cos mt cos omega ct minus sin mt sin omega ct. If we put the value of mt, we'll get this whole expression. Here I've used a Basel's function with n order and argument beta with x of t, and substituting the value, this is the expression. Remember this expression. Okay, it is quite important, this one. Now let's look at the properties. The properties of Basel function is j of minus n beta is minus 1 to the power minus n j n beta. Then it gets reversed from j of minus n beta to j n beta. X of t is j n beta cos omega c plus n cos omega m. The FM spectrum consists of a carrier frequency 9 plus infinite number of sideband at frequency, let's see, plus minus FM. All lines are equally spaced by the modulating frequency, and the odd order lower sideband are reversed in phase and inverted related to the unmodulated carrier. This happens with only the odd order lower sideband. Okay. Now the Bezel's function is 1 upon 2 pi minus pi to pi e to the power jx sine theta minus n theta d theta. These are the very important properties of Bessel function. As the number n increases, Jn x decreases. That means J naught x is the maximum value. I have already talked about this, how to convert from a negative n value to a positive n value. Jn square beta is 1. Jn beta always result in real value. Now consider this example. Consider a tone modulated FM or PM wave with FM 10 kHz, beta 2, AC 100 and FC 30 kHz. Write an expression for FT. Draw a spectrum line, beta 2 and show there from that ST is less than A square by. We know the instantaneous frequency omega I is omega C plus Kmt, where mt is A sin omega mt and d by dt is A by omega m cos omega mt. Omega I is omega C plus K am by omega m cos omega mt. Fi is fc plus K am by fm cos omega mt. Beta is modulation in Kam by fm, where K is 20 kHz. And if we substitute these values, we'll get instantaneous frequency as 30 plus 20 cos 2 pi 20 pi t. If beta is greater, it is a wideband signal. Okay. Now for wideband, we have already known this equation, and beta is KFM. I would suggest you to kindly pause this video and look for a second how I have done, because this is the correct method. You won't get it anywhere. I have done it personally by myself. So have a look at it, understand it, clear your concept, and then move forward. This is again the line spectrum. I've shown all the possible magnitudes. Okay, have a look at it, and you will get all the answers. If you have any query, comment below in the section so that I can get to know and clarify your doubt. Moving forward, we have this transmission bandwidth and distortion. It has been proven that Jn of x decreases as n increases. So, for the major sideband are present between Fc plus minus and Fm. For x less than 1 significant sideband in range Fc plus minus Fm, according to the Carson's rule, dt is 2k plus Fm, which is 2 into Fm, k slash Fm plus 1, 2 Fm d plus 1, where deviation ratio is k by Fm. For a better approximation for equipment design, dt is 2 Fm d plus 2. For PM signal, 2k plus Fm, where 2 m t kp plus 1 Fm. So you can check it out also. I have a confusion in this particular expression, but yeah, the rest of it is correct. Most of the time, first look at for the if the deviation is greater than 1 or less than 1 and doesn't lie in the range of 2 to 10, then its frequency is 2fm d plus 1. Deviation ratio is k by fm, where k is frequency deviation, which we have already, which we know by. So sorry about that extra zooming, but yeah, I was talking about. Look out for the deviation ratio. Deviation ratio that we generally see is by expression 10. Okay, now this is the deviation ratio that we actually see. So this d and this d is equals to del F, you can say so. Moving forward with FM generation by indirect method. The narrowband signal can be modulated by using a DSP-SE modulator. This is a particular expression for NBFM and NBPM. The output of this NBFM also has some magnitude variations. A non-linear device limits the amplitude of a bandpass signal to remove distortion. The hard limiter is often used. For cos theta greater than 0 is 1 and cos theta less than 1 is 0. Moreover, the zero crossing is preserved in the output because with N is there. When the input is 0, the output is also 0. You can see that there is a hard limiter which is passed through a bandpass filter to get the particular signal. Next is the generation of wideband signal. And for generation of wideband signal, we use a frequency multiplier. Frequency multiplier is a non-linear device where the signal is squared and twice of that frequency, twice of its center frequency by passing through a bandpass. What is happening to me? Now, in multiplication where beta is equals to n beta, k is equals to nk, and fc is equals to nfc. Moving with the next, kindly look at this solution question very carefully, and we will be discussing its solution in the preceding slides. So, in the succeeding slides. Now, if you see the I have very clearly illustrated this example clearly to you. Have a look at it. Try to understand it, how it is done and why it is done. And then you will realize that it is much simpler to calculate these in all this when you know how to calculate it. So the local oscillator gets you a frequency of 440 kHz and with M1 and M2 having different numbers. Now a direct method of to generate an FM is being shown in this example. In that, what we use is a bias semiconductor diode that can be used as a capacitor whose capacitance varies with the bias voltage. The omega naught is 1 upon root LC. The variable capacitance is given by this formula. Maximum capacitance variation is twice of del F C naught by 2. I think this would be cancelled out. This method often results in a poor stability parameter. Often a feedback is used to stabilize the frequency. The demodulator, have a look at it. Slope detection, balanced modulator, and zero crossing. It is always in the zero crossings that we find the information. And last but not the least, the FM demodulation with PL. It is used to track the phase and the frequency of the carrier component of the incoming signal. The operation of PLL is similar to the feedback. If the feedback system is not equal to the input signal, the difference will change the feedback signal until it is close to the input signal. The output of the error signal, if the frequency are same of both the input and the VCO signal voltage controlled oscillator, then both are said to be in a lock range. If the phase are same of both the input and the VCO signal, then both are said to be in the capture range. So friends, this was all for today. I hope you liked the lecture slides, and if you like them, please do subscribe to my channel and like the video. Keep on test yourself by solving more and more questions. And for more videos, come on Prepare for Gate channel. Thank you. Have a nice day.